Hi everyone, today we will talk about basics of natural language processing. Natural language processing is a task of machine learning and AI that focuses on processing natural language. So, what is natural language? Talking about natural language is basically the language of humans, the language that humans understand, speak, write, all of that is natural language. Why do we talk about natural language as a separate thing? It's because we also have a term called as programming language. That is the languages that the computers understand, that we write so that the computer can understand that. But in natural language processing, our task is to make the computer understand even the natural language. That is the language that the humans speak. So, on this note, let's start with the basics of natural language processing. I hope you got the idea of natural language. So, let's talk about natural language processing now. What is natural language processing? It's basically the branch of computer science, or more specifically AI, concerned with giving the computers the ability to understand text and spoken words in much the same way human beings can. As we said, the natural language, concerned with giving computers the ability to understand natural language. NLP combines computational linguistics, rule-based modelings of human language with statistical machine learning and deep learning models. Together, these technologies enable computers to process human language in the form of text or voice data and to understand its full meaning, complete with the speaker or writer's intent and sentiment. This last line is actually very much crucial. Complete with the speaker's or writer's intent and sentiment. Normally, when we are working with any NLP task, the issue that we face is like how will the computer understand what is written, and let's say if the computer is able to understand what is written, how will it understand the meaning behind it? Because sometimes in the natural language the meanings are not generally very much clear. For example, let's say what I'm talking about a review of a movie, and let's say I say the movie was not bad, I like that movie. Was that a good review? Was it a positive? Was it a negative? Or was it a neutral review? I would say it was a neutral review because it's not bad as well, but he also liked it. Normally, when we use this word not bad in a human sense, it's like, yeah, it was just okay. But let's say we want the computer to just identify if it was positive or a negative sentiment. I would say it is a positive sentiment because we are not saying anything bad about the movie, but the computer can confuse with that. How will we make the computer understand that this is a bad or a good review? So in NLP, that is something that we solve for. We try to make the computer understand the natural language and identify patterns from them. So let's move on to the other slide, wherein we are talking about the tasks that NLP is working on, the natural language processing task. These tasks are generally described in two forms or are divided into two categories: analysis task and generation task. In analysis task, we have semantic analysis as well as syntactic parsing. In generation task, we have question answering, language generation, and machine translation. Talking about semantics, we have named entity recognition, that is basically extracting entities from a text or from a document. Entity could be an address, organization name, date, person name. There are many entities. Then we have similarity identification, we have text classification, we have topic modeling, we have opinion slash sentiment analysis. All of these tasks come into the semantic analysis part of the natural language processing. Then we have syntactic parsing. In syntactic parsing, we have part of speech tagging. We will talk about part of speech tagging further in this session. Then we have chunking, we have dependency parsing. In generation task, we have question answering. Question answering, the easiest and the well-known example are chatbots. So we use NLP to train chatbots so that they can be much more efficient, much more human-like, and that's the task of NLP that is still under development and under research. Then we have language generation, wherein we have text generation or new words prediction. We can also have, I think you must have seen this new words prediction task in real life when you are writing an email on using Gmail. So when we are writing an email, there are certain recommendations that we get around what should be the next word. So that is language generation, wherein the computer is understanding what we are already writing, and it is predicting and it is providing us recommendation on what should be the next word. Then we have machine translation. Machine translation is basically language translation. For example, English to Spanish, converting textual data or like speech data from English to Spanish, or from Spanish to English, or whichever language possible. That is one of the tasks of NLP that is still also under research. The most common and the most okay, moving forward, we have use cases. So talking about one of the major use cases of natural language processing in the industry, we have smart assistants, for example, okay, Google, for example, Siri, Alexa, these are all smart assistants. We have search results. Google search results are using NLP at some extent for recommendation. We have predictive text. We have language translation, digital phone calls, text analytics, visual assistants, detecting duplicates, social media monitoring, marketing strategies, descriptive analysis, and automatic insights. All of these are use cases of natural language processing that are currently being used in the industry and being developed by fellow NLP engineers. So, apart from this, one of the most common use case of NLP we can see in our emails as well. Again, we talk about emails. So, as you can see, there is a spam mailbox in your Gmail account, right? How does it happen that suddenly you see your spam account filled with certain mails? So what happens is the whenever you receive a mail, it identifies that is that a potential spam mail or not, and it sort out those specific emails as not spam or spam, and then whatever mails which are spam mails are sent to the spam mailbox. That is also a part of natural language processing, wherein the computer identifies the contents of the mail and tells and identifies what is it a spam mail or not. That is one of the most common use cases that we can see in natural language processing. Now, moving forward, let's talk about adoption of NLP in the market. Currently, NLP is having a 14, as per this data, we can see that NLP is having a market share of 14.27 billion US dollars as of 2021, and it is expected at a CAGR, compound annual growth rate, of 27.4% till at 27.4% by 2027, with a market share of 61.03 billion US dollars. That is pretty good, to be honest. And it's one of the most adopted area or a part of AI or subset of AI that is currently being adopted in the market. We have computer vision, we have audio, we have speech recognition. All of these are AI subsets, but NLP is one of the most adopted subset of AI that is currently being, currently there in the market. Then we have automotive, we have government. All of these sectors, we can see there is a predicted growth in the NLP market, and we can see NLP has a very bright future. So moving forward, we have some of the amazing tools for NLP. Uh, we are missing one tool here, that is the Hugging Face toolkit. It is one of the most adopted as well as one of the most used, or you can say one of the most favorite an NLP toolkit out there. We have Spacey, we have NLTK, we have Alan NLP. We have all of these amazing toolkits. You can refer to this Medium blog for some of the open source toolkits. These toolkits are basically the core of what we are doing in NLP. Normally, in industry, we generally go for using these toolkits only to develop our NLP products. Apart from that, there are certain companies which are doing certain researches around the area of NLP. They also use these toolkits to develop their research and to accelerate their research. So moving forward, talking about data cleaning and pre-processing. So here we will be shifting to a notebook that I've maintained for better understanding, so that we can go through the code as well, like what happens. We're talking about something, but what is actually happening in the at the code level, we will talk about that now in data cleaning and pre-processing. So let's move to the code. So this is the NLP Basics IMDb Movie Review Sentiment Notebook that you can refer. You can find the notebook link in the description, or you can find the link at the end of the presentation as well. So moving forward, we have NLP Basic Sentiment Identification from IMDb Movie Reviews. So in this notebook, we will be working with the database as well as understanding the concepts of NLP. So in this we will talk about data cleaning, tokenization, lemmatization, and stemming, that is basically normalization. Then we will talk about pause tagging, word embeddings, vectorization, training a model, and inferencing from the model. Talking about the dataset, we have IMDb dataset having 50K movie reviews for natural language processing or analytics task. You can refer to this link for the dataset. This is a open source dataset, and yeah, let's move forward. Okay, so first of all, importing the required libraries, then we are getting the data. So let's have a look into the dataset now. So looking to this, we can see there are two columns. There is one review and there is one sentiment. And so normally when we are working with NLP tasks, the first thing that we do is to look around the data, to explore the data, that is doing the EDA, exploratory data analysis. So in this, we go through the data set, we identify what all features we are having, what all target features, what is the target value, and what all processing we have to do. We try to identify certain patterns by hand and try to reduce, or try to understand the similarities of different features in a model or in a dataset. Sorry. So here we can see we have these two columns, review and sentiment. These are all, both of them are textual dataset. We can see that because yeah, it's text. All of these are text, but the computer doesn't understand text. So we will eventually convert all of these into numerical values. So let's first do a bit exploration. We will not do a detailed EDA here, just a quick look into the data set, and then we will move forward to the concepts. So in this we have data, we are just calling this function. You can see there are 50 values, unique are 49582. That means we have certain duplicates. Then we have two unique value in the sentiment column, and yeah, then we have the data.info. You can see that both of the columns are not null. That means there is no null value, so we don't have to do any null removal. We will talk all about this in data cleaning. It's basically exploring. We are seeing that okay, there are these many values, and this is the data type of the data set. In pandas, this is basically pandas. In pandas, when we are working with a text data, it's basically having it has a data type of object. Then we can see we're calling this function to check what are the unique values. So it's a pretty balanced data set. We have 25,000 positive as well as 25,000 negative values. Moving forward, let's talk about data cleaning now. So data cleaning is a task of removing unwanted data that could affect our final prediction, as well as removing null values. Null values are basically no value, as in no value is maintained for a specific field at a specific row. So data cleaning includes removing these null values, removing duplicate values, We also do lowering text or to normalize the text. We remove punctuations. Basically, the task of data cleaning is to remove unwanted data. That is the data that we do not want to be even a part of our data set. So when we're working with NLP, punctuations as well as stop words are some of the data that we do not actually require. That is depending upon the scenario or the problem that we are solving. In terms of uh, basics of NLP, we generally do not require these stop words. Stop words are the words that are present in abundance in a string and can be deceiving for the model or tricky for the model. For example, in, at, the, these are some of the most common words, yet they are present in abundance and can confuse the model. So we refrain from keeping these stop words in our data set in the text corpus. So we will be removing the punctuations, we will be removing the stop words. We'll also lower the text so that it is normalized, so that every word is so the main concept around using this doing this normalization is, for example, let's say we have two words. One is in capitals. For example, we have the is one of the word. It is maintained. There is a scenario wherein the first letter of the, that is T, is capital, and there is a scenario that in the text only we have the, which all small case. In this scenario, what happens is, when we are working with the data, the computer might take those two words and like understand those two words separately. It might although the both of those words are same, but the computer might understand that these two are separate words. So to make them normal, to generalize or to normalize that so that the text is the text casing is similar all over the text corpus, so that the computer doesn't confuse with similar words having different case. So we are really lowering the text as well. So this is the whole code for removing the duplicate. So here we can see the duplicate values. So these are all the duplicate reviews, and here we are dropping those duplicate values from our database. After doing that, we can see that we have the unique and the count is same, 49582, 49582. Sentiment is 2. That's basically, we can see that the duplicate values are dropped. Now we will be removing the punctuations. So basically, we are removing we are using this function to remove the punctuations. So when we are seeing the data set, we can see that in the review, we can see that the punctuations are removed from all of these reviews. So let's say, for example, let's take an example. Beautiful, not this. Yeah. So let's see. Let's say talk about there. So basically, there's a family where a little boy. This is the sentence here, right? So there's, and this the apostrophe is our punctuations, and it's punctuation. Let's see. So yeah, basically there is a family. So you can see the punctuation is removed from the data set. Now we will remove the stop words. So after doing that, after performing this text, you can go through all of these functions. It is a public notebook. You will be having access to this. You can go through the code. If you have any questions, you can ask in the comments, or you can reach out to me on LinkedIn as well. So we are using these functions to remove the stop word, as we can see. So let's take an example. Let's say, okay, quite not this one, sorry. Yeah, a wonderful little production. So in this, is stop word. So let's see. Yeah, you can see is removed. So we can see that all the stop words have been removed from our data set now. So as we can see, let's say I did certain EDA and I identified, okay, this much only cleaning was required for the data set. And basically, we identify what all cleaning is required. We do it via EDA. We explore the data set, and then we identify what all things needs to be cleared from the data set. For now, we are we're just removing the stop words, punctuations, and lowering the whole text. I'm lowering the whole text here only, and yeah. So moving forward, let's talk about tokenization. Tokenization is converting data into small tokens. In case of natural language, string of text is divided into substrings. Those substrings could be words, that we call as word level tokenization, letters, character level tokenization, sentences, sentence level tokenization. Then there is also a tokenization we call as n-gram tokenization. So, yeah, in n-gram tokenization, we basically tokenize a whole sentence into pairs. In bigram, we have pair of 2 words. In trigram, we have a pair of 3 words, and more on. So, let's talk about word level tokenization. In word level tokenization, let's say a string is my name is Sambhav. So the token after tokenization, the string will become a list of the tokens. My is one token, name is one token, is one token, and Sambhav is one token. Here, each word is a single token. Now let's talk about character level tokenization. So let's say the string is my name is Sambhav. So after character level tokenization, the tokens will be M is a separate token, Y is a separate token, and every character, every letter would be a separate token. This is a character level token. This is character level tokenization. Then sentence level tokenization. So let's say we have a paragraph. Let's say in this scenario we have this string that is having 2 sentences. My name is Sambhav. I am an NLP engineer. Tokens will be the first is the first sentence. My name is Sambhav, and the second is I am an NLP engineer. Then moving on to n-gram tokenization. Talking about bigram tokenization. Let's say our string is my name is Sambhav. The tokens will be my name is one token, name is another, is Sambhav is another. In trigram, same for the same string, tokens will be my name is one, and name is Sambhav is the another, is the next token. This is tokenization, wherein we divided our string into substrings. So this is a basically a very crucial task in NLP that we do. It's actually the first thing, or one of the major things that basically we do for our NLP task is basically to identify first of all, to identify what kind of tokenization that we need to do for our model to learn at the best possible way, and which level of tokenization can solve our problem. That is the first thing that we try to identify when we are starting with pre-processing of NLP, of the text corpus. So here we will be tokenizing using word tokenizer from NLTK package. So I have imported this word tokenize from the NLTK package, and I am applying this tokenize on every textual string. So I'm applying tokenization of this separately and all. So as you can see, after tokenization, the tokens have we have received the tokens. We are doing word level tokenization. So the string one reviews mentioned watching one OZ episode is now one reviewers mentioned watching. These are all now separate tokens. We have also maintained the token length. This is basically it will be used later on. It's not a concern as of now, but just maintain it for further. So it's so we got 167 tokens in this line. We got 84 tokens. We got 84 tokens in the next one. Then let's have a look into the data set. We saw that okay, the count is same, and the mean length is 120. All of this information will be used later on. It will be helpful later on when we move forward in our pre-processing tasks. So the next component of pre-processing is padding. Now, padding refers to padding this padding the sequences so that every sequence is of same length. Padding means addition of certain token or certain value to the sequence. So let's say as we see, right, as we saw that there are 167 tokens, there are 84 tokens, there are 88 tokens. What we try to do in padding is we pad these sequences, or we add a specific token at the end or at the starting of the sequence, so that the token length is similar for all of the tokens. This is required for in NLP, because when we are working, specifically when we are working with neural networks, our input is predefined. We define our input beforehand, and the input is constant throughout our model. So to achieve, like to attain that the constant value, right? We need to maintain a specific token length. So for example, let's say we have this 167 token length. Let's say this is the input to the model. It is of 167 length. Now the next input is of 84 length. We have a variation. We have a variation in the text in the token length. That is not that this basically will not be good when we are working with when we are working with neural networks, because we cannot provide a variable length sequences to a neural network. So for that task we do padding. So padding is basically a two action task wherein we either add value or we remove value. So, taking an example, let's say we have this token length of 167, and we want our sequences or tokens to be a length of just 120. So, for this scenario, in this scenario, we will remove certain tokens from this sequence, so that the token length is now 120. Or let's say in this scenario wherein the token length is less than 120, we will add certain tokens to this sequence so that the token length will become 120. So in padding, we normally do either add a value or remove a value. After tokenization, in order to maintain same length for every sequence of token, either a value is added at the end or at the beginning of the sequence to increase the length or decrease the length of the sequence by removing the tokens from either from the start or the end, to basically have a generalized a constant length sequence data. So in this scenario, we are maintaining our max length as 121. We are padding the tokens. This function, we are using this function to pad the tokens. We are adding the end token to pad our sequences. So let's see. Let's have a look into the data set. So for example, this we have this sequence. In this sequence, we only had words till this word planet, and it is smaller than the max length, so we added these tokens until we had a length of 120. This is what we do in padding. Moving forward to normalization. For grammatical reasons, documents are going to use different forms of words such as organize, organizes, and organizing. These are all the same words, but used separately to work out the word, to keep the tenses in check, to keep the grammar in check, basically. But both all of these three words, they are having the same meaning, or they would say the same. They are having the same root word, that is organize. Okay. Additionally, there are families of derivationally related words with similar meaning, such as democracy, democratic, democratization. In these scenarios, the word is having the same meaning but different spellings. So to remove this scenario wherein the word is having the same meaning but different spelling, we normalize those words to its root word. In root word, we normally call as the stem word as well, or the base word. So, okay, continuing where we left. In many situations, it seems as if it would be useful for a search for one of these words to return documents that contain another word in the set. It's basically saying that we convert these words to to a single word that basically describes all of these uh, and have the same meaning as all of these. So, for example, in these, I think democracy has the same meaning as democratic. Democratic has the same meaning as democracy. Democratization has the same meaning as democracy. To cater the above situation, the most common approaches that we will look into in this session is lemmatization and stemming. The root word is called as stem in stemming and lemma in lemmatization. The goal of both stemming and lemmatization is to reduce forms of a word to a common base form. For example, running, ran, run all has a base form as run. So we convert these words to a base form so that the meaning it has a similar so the computer can understand that all of these words have a similar meaning. So let's talk about lemmatization. The major difference between lemmatization and stemming is lemmatization is the process of reducing words to their root forms, such as mapping a group of words to the same lemma if the lemma itself is a valid word in the language. This is the major difference between lemmatization and stemming. Lemmatization keeps in check that the word is a valid word in the language, but stemming does not care about that. In stemming, it doesn't matter if the root word that we have derived is a valid word or not. We'll look into that. So let's first look into the lemmatization. I'm using a word lemmatizer from the NLTK package. We're using this function. After lemmatization, we got these values. For this token, we have the lemma of the token. So as you can see, one reviewers reviewer is turned to reviewers is turned to reviewer. Watching, mentioned, watching, all of these are words that are already there in the language, so that's why they are not they haven't been reduced. uh, so as you can see, in lemmatization, if the word is a valid word, it basically checks if the lemma is a valid word or not. So you can see, we will see the major difference in lemmatization and stemming when we talk about stemming. You can see the major difference in the output of the derived words. So in this, we can see that there is not a big difference in the in the words after lemmatization. But now let's go to stemming, and then we can come back to this and we can check the difference as well now. And so stemming is the process of reducing inflection in words to their root forms, such as mapping a group of words to the same stem, even if the stem itself is not a valid word in the language. So here's the main difference that as we talked about, is that the word, the derived word, or the stem word may not be a valid word in the language, and that's okay when we are working with stem. So maybe I'm using a Porter stemmer here. I'm using the Porter stemmer from the NLTK package. After stemming, we got these words, we got these tokens. So this is the token and this is the stem tokens. So one is one, reviewers has been stemmed, has been converted to review, mention to mention. Here, as we can see, there is a huge difference between stemming and lemmatization. And that is actually depending upon our tasks, what all tasks we are working with, we try to use lemmatization or stemming. Now coming on to the difference, right, as you talked about, there is a huge difference, that is the word may or may not be a valid word in the language. So as you can see, for example, this word little is converted to LITTL. That is not actually a valid word in our language. But when you go to lemmatization, the little word is still little. It's because it is a valid word. That is the major difference when you're working with stemming and lemmatization. When we're solving any problem in NLP, we have to identify it ourselves. We do certain EDAs and all. We do the EDA and identify what is our requirement, and on that basis, we try to identify which normalization step we should be using. Should we go for lemmatization or stemming? Then moving on to pause tagging. Pause tagging is basically part of speech tagging that refers to classifying words in a sentence into their part of speech. So what is part of speech? Part of speech, I will show it to you. Basically, nouns, adjectives, verbs, all of these are part of speech. So we identify the tokens uh, part, or basically we try to identify uh, what basically what this token is in the whole in this whole sequence. So is it a noun? Is it a number? Is it an adjective? Is it a verb? That is something that we try to identify. We try to identify what is the part of speech this word refers to. Is it a noun? Is it an adjective? Is it a verb? Uh, and many more. We have different tag sets as per our requirement. So moving back to like part of speech are also known as word classes or lexical categories. The collection of tags used for a particular task is known as tag set. These tag sets can be there are multiple tag sets. Depending upon our usage, we tend to use the specific tag set. So in this scenario, I'm using a universal tag set. In the universal tag set, we have a less amount of pause tags, but it all depends upon what type of problem you're trying to solve and what you have identified after doing the EDA. So in this, I'm using universal pause tagging, and you can also try some other tag sets. You can refer the NLTK the NLTK documentations for other tag sets that you can use. So yeah, moving forward. Okay, before moving forward, let's talk about the need of part of speech tracking. Part of speech tracking is, you can say, can also is basically first of all to understand the data set. To let's say we are doing some name entity recognition, we can do certain analysis that okay, this word or this entity is always a noun. It always comes after an adjective. It always comes after or before a verb, or etc. Whatever you want to identify, you can do that at a at a like at a literally at a linguistic level. If you want to identify certain patterns, you can do that using pause tags. Pause tag can also be a feature for a model. So when we are doing certain feature engineering, pause tag can also be one of the features for a model to learn to identify patterns from. Now moving forward to word embeddings. Word embeddings describe a specific word with number. Basically, it defines certain we define certain word with number of values with numericals, basically. So okay, I will come back to that. First, let's continue. So pre-trained word embeddings as a game changer as they provide a push to the model. Pre-trained word embeddings could be contextual or non-contextual. So first of all, let's see what is contextual. Then we'll see what is non-contextual word embeddings. Contextual word embeddings are those word embeddings which are trained in such a way that the context of the sentence, the string, has been taken into account. So let's take an example. Contextual word embeddings are, let's say, our model. We have trained these word embeddings in such a way that we are also learning the context of the whole sentence. For example, let's say our sentence is, my name is Sambhav and I am a NLP engineer. In here in this we have these two sentences. We have this my name is Sambhav, and then I'm saying I am an NLP engineer. So the context here is that is referring to Sambhav, who is an NLP engineer. So in this scenario, we can see that I is basically Sambhav itself. That is the context of I. So we are saying I am Sambhav Garg, and Sambhav Garg is a natural language processing engineer. That is basically learning the context. So in this scenario, our embeddings are trained in such a way that the context is learned as well. Whereas when we are moving on to non-contextual word embeddings, wherein the context is not taken into account, is for example is learned in such a way. For example, we try to identify which all word pairs are the most frequent. This is an example of the glove embeddings. You can read about glove embeddings, and so those embeddings are trained in such a way that it is basically learning how much frequent those words, a word is coming in pair with other words. In such a scenario, it tries to identify the relation of the word with other words and try to put a number or try to define a specific word with numerical values. These numerical values are not a single word, a single number. It could be a vector or a matrix of numbers. So as we mentioned, right, we are defining a word with numbers, and these numbers are learned either contextually or non-contextually. So one of the major example of contextual word embeddings are the BERT word embeddings or LSTM word embeddings. And in case of non-contextual word embeddings, we have examples like glove word embedding or word to vec word embeddings. These word embeddings tend to give actually a very good push to a model to learn specific patterns, because they basically provide insight around the whole text. They provide insights around the whole words or around the tokens that we are already having, that we are training for the model to identify such certain patterns from them. So after doing all the, you can go through the code separately. After going through all of this code, we got certain word embedding. So here we actually am using glove word embedding. So you can see in the data, I have kept this data set wherein we have the text files. Yeah, so as you can see, right, in the text file we have the word and their respective numerical values. So for example, the is having these, is basically, you can say, can be defined with these numerical values. It's basically, we are no in machine learning terms we call them as embeddings. Embeddings are basically features of that specific word. So these are all the features of the specific word or the specific token. So let's, for this token we have all these features. It's basically described by these numbers and all. So this is what we are using now, using the glove word embeddings, and we will extract the word embeddings of all the words. For example, I'm getting the fairy tale fantasy. If this word is there in the glove embeddings, we will extract those embeddings. If not, it will assign certain random value to this as a word embedding. So why am I assigning a random value? I'm assigning a random value so that when the model is training, it will try to learn the embeddings of this word as well. Randomization is basically, it might help for the model, not as per as at a level at word embeddings, but randomization is basically initialization of word, so that the model tries to learn and it will try to improve these or learn these numerical features as per our requirement, as per the problem. Okay. Now let's move on to vectorization. Vectorization is basically a task of converting the textual data or the tokens to a numerical value. Why we do that is basically because computers doesn't understand text; they understand numerical values. So we convert all of those tokens to a specific numerical value. Vectorization of a textual data can be done in multiple ways. Most of the common vectorizers are bag of word vectorizer. When we are working with sklearn, there is a count vectorizer, that is basically a bag of words vectorizer. Then we have a TF-IDF, term frequency inverse document frequency vectorizer. Then we have custom vectorizer. All of these vectorizers have their own purpose. They can be used as per the requirement. We can identify which vectorizer to use either by trial, hit and trial, or as per the requirements. For example, the custom vectorizer, they are generally used in scenario when we are working with deep neural network. In that scenario, we basically vectorize our tokens as a unique integer value. In that scenario, we are not vectorizing it on the basis of its count or on the basis of its frequency as compared to the whole document. So in bag of words or count vectorizer, we try to vectorize the word as on the basis of the occurrence or number of occurrence or count of the word in the corpus. Whereas in TF-IDF, we talk about the frequency of the term over the frequency of the term within the whole document. This is something that you can go through. I think we talking in depth around all of these concepts would be a bit of time consuming, but I would say we can go through all of these. Is readily available on the internet. It's openly available and it's easy to access. And yeah, moving forward. So here I'm using a count vectorizer. We got after performing the vectorization, I'm training the vectorizer on the lemma tokens that we got above. Then we got the shape. We got that. Okay, this is the shape of the vector. For 49582 sequences, we have 14181 vectors. Now, you can learn about count vectorizer is basically 141851. It has 141851 unique words, unique tokens here. For all of those, we have the count of that word in that specific review or in the specific token or in the specific sequence. So, for example, let's say we have this sequence, one reviewer mentioned watching. So, there is also wonderful is also one of the words, one of the token, but wonderful is not there in this sequence. So, in this sequence, the count of wonderful will be 0, the count of 1 will be 1, reviewer will be 1, mentioned will be 1, and so on. That is what the count vectorizer is giving us as an output. Now here I'm also vectorizing the labels. Since our labels were in text format, we have to vectorize them so that the computer can understand those sentiments. Or so I'm describing. I'm basically converting them into either 1 or 0. 1 being positive, 0 being negative. Since it is just a binary classification problem. Binary classification problem. I hope you understand what is a binary classification problem. We will not go into in depth around that. So yeah, moving forward. So that was basically our pre-processing task, basic pre-processing that we do generally in any NLP task: tokenization, padding, vectorization, lemmatization, stemming. So all of that was part of our pre-processing. Now we will move on to identifying and training a model. To identify the model, EDA needs to be done on the data and as we mentioned earlier, EDA helps in narrowing down the search space for a model selection for training. So normally, as we say, identifying the best model, there is no such best model for any such scenarios. In generally, we do hit and trial to identify which model would perform best in our scenario. But to narrow down that search space, we go through the data set, we do certain EDA around the data set so that we have a very narrow search space wherein we will do our hit and trial. Now, since the current task is a binary classification problem, we will just be using a logistic regression algorithm for training. Many other models can also be used to produce better results. I'm not saying this logistic regression is the best solution here. There are many other models that we can use to train our models. For the presentation sake, we are using logistic regression here. So first of all, we are dividing the data set into validation as well as training data set. So we will train as well as validate. I think in this scenario, we are not working on validation. Validation is a whole other concept. Here we are dividing the data set into training and testing. So we will train over these many data set, these many values or line items, and we will test around these line items. So herein it's pretty simple. Herein we are fitting the whole model. After training, we go to the inference. Inference is basically the task of generating results, and inference is using the trained model. So we predicted, we are using this code block to predict values for the test data set. We got the predictions. Then we will check for the mean accuracy in F1. So we can see the mean accuracy is 0.867 and the F1 score is 0.869. That is pretty average. Then here we are checking for a specific text. So let's say this movie was one of the best I watched in recent times. This is a positive sentiment, so it should be 1. Yeah, it is 1. then this movie was not bad and I really liked it. This is also a positive sentiment. I think we have talked about this the start as well, right? But here, as you can see, the model is splitting it as negative. Why is that? Let's try to understand what we did before training the model. We vectorized the model on the basis of count. That means in a review, if the count of a certain specific sentiment word is more, it can bias the output to the specific sentiment, like at the cost of the actual intent of that specific review. Then let's go to the. We'll talk about this and how we can how we tackle this, and I will show to you how we can understand uh, like beforehand to like not face such a scenario. So let's say let's look at the other example as well. The cinematics of this movie made my eyes bleed. It's a pretty sarcastic comment, and I can see that the model is also predicting it as negative. I think the word bleed would have been a very good impact on that. But yeah, so this is what we got from predictions using the logistical regression model. Now, I will show you this word cloud that we normally create in when we are doing an EDA. So in this you can see that the word film, the word one, even, show. So these are one of the most common words. But if you go through this specific word cloud, we can also see there is word good, there is word bad. That are also pretty much common in one of our reviews. So these words tend to bias our sentiment of the specific sentence to a specific sentiment. So in this scenario, we try to actually this is the major reason that we try to train the sentiment analysis models using using a recurrent learning model or a transformer maze model, which generally we generally work with contextual word embeddings and try to identify the context of the whole sentence. So I will show you an example of a Hugging Face model that I am training here on the same data set, and we will check out the prediction from that. Now, okay, let's read this. The inability of these classical machine learning models to identify the context of the text is the reason that recurrent neural networks and transformer-based models are the most widely used models for such tasks, as they tend to understand the context of the text better. Below, we will be training a Hugging Face model. So I will not go through the whole code. You can go through the code separately in this slide in this notebook. Let's move directly straight towards the predictions. So let's see. So the first sentence is, this movie was one of the best I watched in the recent times. It is label one, that is positive. That's good. This movie was not bad and I really liked it. This is also one. As you can see, the difference here as compared to the classical machine learning algorithm that we use, the logistic regression, and the Hugging Face model, is that it has also understood the context of it, that it is not bad. It is not just bad, it is not bad. That's why it is able to understand that this specific review, it's actually a positive review. Then it is also able to understand that the sarcastic review and predicts as negative. So overall, we have understood what are some of the basic concepts of natural language processing, what all reprocessing, what all data cleaning we do when we are working with an NLP model or an NLP task. And we also understood certain contextual and non-contextual scenarios that we might face when we are working with certain problems. So that is it for this session. Thank you, everyone. Thank you for listening.